Good afternoon, everyone. Welcome to today's presentation. My name is Dr. Yao Yevenyo Ziggah. I'm a senior lecturer at the Geodetic Engineering Department, University of Mines and Technology. Today, I have the privilege and honor to present on the benefit of artificial intelligence for geodetic coordinate transformation. And I'm honored that the WAIMM organization has given me the platform to be able to do a presentation on this topic and also share ideas with participants and students who have joined both in Ghana and far in other countries. So my presentation is going to start with introduction. We'll go through some conventional transformation processes, the challenges with the conventional models, why we need AI for coordinate transformation, the AI transformation procedure, the applied AI methods that have been used in literature so far, and then a demonstration of some case studies, both in Africa and then across the globe. And then we move to the conclusions and then the future directions. First of all, before we can move to today's presentation, there is a need for us to understand the three pillars of geodesy. When we talk of geodesy, it's a branch of geomatic engineering where the focus is actually to measure, to take measurement on the surface of the earth, to understand the gravity field, how it varies with time, to understand the rotational aspect of the earth, and then also to propose a well-defined coordinate system that can help us practice as surveyors or geospatial engineers. Now, we know in our everyday life that whatever we are doing as earth scientists or geoscientists, or even as professionals within the built environment, we use coordinates. We cannot do anything without using coordinates. Whether we work in the mine, before the mine engineer or the mine planner can do his or her weekly mine schedule, there is a need for the mining engineer to get hold of the coordinates or the information that the surveyor has picked from the pits and will supply it to the mining engineer. So the same way, if we want to mine the minerals that is found within the in-situ rock, even after blasting, there is a need for the surveyor to set out the ore block for the mine operations department to carry out mining. When you go into road construction, we still need the surveyors to be there, because you first of all need to understand the topography before you can even do the design. When it comes to building, it's the same. We do the topographic survey, we supply it to the architect so that he can orient the building design that he has done to suit the topography. So you realize that within the geosciences, whether you like it or not, it's coordinate that controls all the affairs that we are doing. However, do we really understand the coordinate we are using? And why do we need to even do what we call transformation? So the reference frames that you see there is actually the control point that we've built, the monument that we've built, where we fix our GPS on it to help us to be able to achieve our working target. So be it an environmental person, if you want to map out an accident area, there is a need for you to use coordinates to pick the information, and then you add other controlling factors for you to even design or to give a spatial distribution map. So you notice that whatever we do, we use coordinates. So it is very important for us to understand why we do, or why there is the need for us to understand what coordinate transformation is. Now, in our daily activities, now in the mine, you realize that they are using drones. They fly the drones, they will pick GCPs, ground control point. Why are they picking ground control points? Because they want the image to be transformed to fit into the mine site. What they are doing is also coordinate transformation, but just that it is on a smaller scale. And this is more of image. So we say they are doing georeferencing. So coordinate transformation is something that we do in our daily activities that we may not even know that we are doing transformation. And when we talk of transformation, you are looking at two coordinate systems. So now I will talk in respect of looking at the global and then the local. Now, we know that with the advent of GNSS technology, everybody has moved from the classical surveying procedures, which are time-consuming and labor-intensive, to the use of satellite technology. For example, the GNSS. Now, the GNSS, the ones that we mostly know is the GPS. Now, we need to ask ourselves, what is the reference system that the GPS was built on? The GPS was built on a global reference datum. And that global reference datum is what we see in our software. It's called the WGS84. Now, the WGS84, which the GPS was built on, is actually a global datum. Now, when you come back to Ghana, what is our reference mapping system? That is the War Office 1926 ellipsoid. So when you look at the WGS84, which is a global datum, and you look at our War Office, which is a localized reference ellipsoid, it tells you that these two systems are not even the same. And they are not the same in what aspect? You must see that, okay, in terms of their positions, their central point, the origin, are they coinciding? No, because when you look at the ellipsoidal parameters of the War Office and the ellipsoidal parameters of WGS84, you realize that there is a difference. And that should even tell you that before we can use the GPS acquired data, which is based on a global datum, to fit into our localized system, which is the War Office ellipsoid, there is a need to be able to transfer coordinates from the GPS system onto the War Office system. Now, the process of using mathematical relationships to describe or to connect a function between the global system, which is the WGS84, and that of the local system, which is the War Office that we are using in Ghana, that process is what we call coordinate transformation. Now, when you look at the diagram that has been displayed, you will see that we have two coordinate systems here. One is Z1, X1, and then Y1. The other one is Z2, X2, and Y2. Now, when you look at their origins here, you will notice that they are having different origin. So the reference axis 1 and reference axis 2 are having different origin. And since they are having different origins, it means that if you want to use the coordinate in system 2, in system 1, there is a need to bring their origin together. They must meet at a point. And when they meet at a point, you must make sure that the reference axis, as we see here, the Z's, have also met and they are in line. And then we have to also make sure that there is no tilt between these two systems. And that is why when the surveyors pick the data using their GPS, especially when they are doing static survey, you realize that in the datum, in the data processing procedure, you will input certain transformation parameters, TX, TY, TZ, RX, RY, RZ, and then S. These parameters that you are feeding into the system are actually transformation parameters that are helping you to be able to use the coordinate you've picked in a global system in our localized system. So most countries, even worldwide, they all started from a localized geodetic reference network. Then when GPS came, they moved from the localized geodetic network into a more global phenomenon or system. And that is why in some quarters, they will tell you that the WGS84 is a geocentric system, and then the War Office, as we use in Ghana, is a non-geocentric system, because our War Office, the origin does not coincide with the center of gravity of the Earth, or in a layman's explanation, we will say the center of the Earth. Our reference axis, the z-axis, does not coincide with the Earth rotational pole. So all these things, because we lack these with respect to our localized system, as compared to when a system is global, there's a need to do transformation. And we have been doing it almost all the time. When we pick our data in GPS and data is in UTM system or in the WGS84 system, we use transformation parameters to be able to transform so that we can get our localized coordinates. So most African countries are yet to move into a geocentric datum of reference for surveying. So what is happening is that when they pick the data, there is a need for them to do a transformation. So the concept of coordinate transformation is very simple. We want to determine a set of parameters that can help us to bring a coordinate system which is in a globalized system into our local geodetic network. To do that, you need the parameters. So the translation parameters, the rotation parameters, and the scale factor are actually the parameters that defines coordinate transformation for us, because the translation parameters will help us to make sure that the origin of the two reference systems can coincide now. And then the reference axis to, we can use the rotational parameters to avoid any tilt that might have happened when we are moving the system to the other. And then also we use the scale factor to make sure that the reference axes are equal in length. Now that we've talked about the concept of coordinate transformation, we should look at some of the conventional transformation models. These are some of the widely used in literature. The most popular among this, we will talk about the Besser-Wolf. We have the geocentric translation model, which is a 3-parameter. We can talk about the Helmet transformation, the standard Molodensky, Featherstone, and Vanecek, and it goes on and on. But the most commonly used that you find in literature or for most organizations, you see they use the Helmet, the Besser-Wolf, and then the Molodensky bedcast. But all these conventional models that have been proposed are based on different computational procedures. For example, Besser-Wolf, when you use it in a smaller area, the transformation parameters that you are determined, the adjusted parameters, are said to be correlated. So they prefer using the Molodensky bedcast for smaller areas as compared to the Besser-Wolf. Now the Helmet, at a point, they realize that it's more or less like an iterative system. Then the Besser-Wolf gives us a closed form solution of the Helmet. So all these methods were proposed based on certain computational deficiencies that has been shown in other methods. So the idea is to improve it. Now, when you look at the Vanecek and Steve's, Featherstone and Vanecek, they were looking at the aspect where the local geodetic height has not been determined or is assumed not to be accurate. Therefore, when you are doing the transformation, there is a need to avoid using the local geodetic height in the process. So all these methods were proposed based on certain deficiencies in one or two of the methods. For example, again, when you look at the geocentric translation model here is considering only translation parameters. The system is assuming that the reference axes are parallel to each other. There's no rotational effect. It is only the distances apart that they need to consider. So when you look at the geocentric translation model, which is considering only 3 parameters concentrated on the translation, the distances among the axes, what happens with the scale factor? What happens with the rotations? So these are some of the commonly used methods in literature. Now let's look at the conventional models, the transformation procedure. First of all, before you can perform coordinate transformation, there is a need for you to have what we call common points. So now let's give a typical scenario. I work in a mine, and the mine is using its own coordinate system. That is different from what we are using in Ghana. Now, if the mine wants to send a document to the Survey and Mapping Division, Lands Commission for approval, there is a need for them to transform their mine grade coordinate into the national coordinate. So this, in order for them to do that, first of all, they should have common point information. So common point means that if I have control point A, as an example, I should have latitude, longitude, ellipsoidal height in WGS 84, and then I should have corresponding latitude, longitude, ellipsoidal height in the other system. So if you are looking at a grade system like the mine system, the mine grade system, the mining company must have the corresponding Ghana national grade coordinate of all their mine grade coordinates. And that is how come they can apply the transformation formulas to determine parameters and use it to perform transformation. So before you can perform transformation, the first point of call is for you to have common point coordinate. And common point means that one control point, you have two different coordinates that has been recorded on it. So assuming I want to transform coordinate from the WGS 84 to the Ghana War Office system, for control point A, I have to get WGS 84 observed coordinate, and I must get the corresponding observed coordinate in the War Office as well. So that is the common point. So that's the first point. So when you look at this flowchart, you see that we have War Office geodetic coordinates in latitude, longitude, ellipsoidal height, and then we have the corresponding WGS 84. Now, the next step is for you to do what we call the forward conversion. You must convert the latitude, longitude, ellipsoidal height coordinate into Cartesian XYZ system. Now, the moment you do for these two common point coordinates, the next is for you to apply your transformation algorithm. So over here, if it is the Bessa-Wolf you are using, then you must now apply the Bessa-Wolf transformation algorithm, and then you determine the parameters. When you determine the parameters, you now apply the parameters to transform the coordinates that you want to bring into the other system. So for example, if I want to push the WGS 84 into the War Office, then I have to use the parameters to transform the WGS 84 coordinate into the War Office system. But you will agree with me that it is extremely difficult to work on the ellipsoid because the ellipsoid is a curved surface. And for surveyors to be able to work with ease and also convenience, there is a need to move from the ellipsoidal system onto a flat surface. So what you do is that when you now apply the transformation parameters to transform the coordinates, you are going to get XYZ, which has been transformed. Now this XYZ must now be reversed to get it corresponding latitude, longitude, ellipsoidal height. And the moment you get the corresponding latitude, longitude, ellipsoidal height, you do the projection to bring it onto the type of projection that you use in your country. So Ghana, we use the transverse Mercator. So we project the latitude, longitude, ellipsoidal height that we got from the reverse convention and push it onto the transverse Mercator. And this is how we can get our eastings and northerns coordinates. Then from there, if there are existing coordinates available, we compare with them and then do statistical analysis. So basically, the first step, as I've talked about from the flowchart, is for you to use this formula to be able to do the forward conversion. Majority of the softwares that we use to process GPS, at the back end, this is the code that they've written to be able to do that. So you have the X, the Y, the Z, the N, radius of curvature in the prime vertical, which is given by the semi-major axis divided by 1 minus the eccentricity, then sine of what? The latitude. So this is the formula that you use for the forward conversion as the first stage. Then the next is, for example, you want to use the Bessa-Wolf. This is a compact representation of the Bessa-Wolf model. So when you expand it and then you express it in a least squares form, you are going to get an expression like this. And usually the geodesist will say that you can say A transpose A all inverse A transpose L, where this matrix here is the A, this one is the X, the unknown that you want to determine. Then the coordinate XYZ in datum 2 minus XYZ in datum 1, you subtract, and then you get your L. So basically, this is what you do. Then when you get your parameters, you now perform the transformation. Now, what are some of the challenges that we face in applying these transformation models? Now, over the years, scholars have identified that due to how the local geodetic network was established at a time that there was no GPS and classical system of survey were used to establish it, there is a little bit of distortions in the local system. Because of that, the conventional models find it difficult to actually absorb more of the heterogeneity that is existing in the system. Some of the methods too, you need to linearize nonlinear equations by applying Taylor series, which is also time consuming, because the moment you apply Taylor series on an equation to linearize it, then it becomes an iterative solution. And even when you guess the initial approximation wrongly, then the system becomes computationally expensive. And it has also been reported that we do not normally achieve satisfactory results always because of its inability to be able to handle the deformation existing in the local geodetic network. A typical example, for example, when we take the War Office ellipsoid that we use in Ghana, if you look at how it was established, in the southern part, they used triangulation. In the northern part, they used the T-traversing to establish it. Now, when you look at these two different surveying techniques, different personnel, different equipment, different assumptions that they have to use, when you box these two methods together and you use it to form the network, this gives you distortion. And that is why one of the key factors to consider when you are applying any transformation model is for you to understand where the distortion is coming from. Is the distortion coming from the local geodetic network? Is it 1D, 2D, or 3D network that you are considering? So it's one of the key indicators that we consider in order to be able to select the appropriate transformation model to use. Now, why do we need to use the AI? Now, in literature, Bassi in 2002 actually started using the ANN to perform coordinate transformation. Then later on, the Turkish also picked it up, and now almost everybody is trying to use it to improve their transformation accuracy. On the whole, the AI came in, or the most important of it all is that we want to improve transformation accuracy. That is all that we want to do. So when you look at the AI do not determine transformation parameters. The AI do not need any prior knowledge to have a mathematical relationship between the two reference systems that you are considering. So when you look at the classical approach, first of all, there is a mathematical formula that has been established that put together or map the reference system 1 and reference system 2 together. And then in the course of determining parameters, also, you notice that if your geodetic network is highly distorted, it contributes also to the parameter estimation process and the errors that are supposed to be incurred after the parameters have been determined. Now, the AI avoids these processes. Another advantage is that the AI is more of stochastic process. Stochastic here means that the system is able to adjust to the data, is able to learn to identify hidden patterns in the data than being more of a deterministic type, like the conventional models. The deterministic here is that we have all done regression before. If I give you 20 points and then you perform regression on it, you can perform regression 20 times on the 20 points and you are going to get the same answer. That's the deterministic that I want to refer here. But when you take the AI, which is more of stochastic, you can control certain parameters in it, fine-tune it to be able to give you the desired result that you need. And when you look at the computational processes of most of the AI, you will notice that the system is always pushing to compare with the desired result or the loss function or the fitness function that you want to get. And at the end of the day, you realize that the system can actually train itself or calibrate itself on the data to arrive at the result that you need. Now, if we look at the process that we go through when we are using the classical method, in the classical method, the first stage, you have to do the forward convention. After the forward convention, you apply the transformation formula on it. You determine the parameters. After determining the parameters, you perform coordinate transformation on the data where you want to push the data to the system. Then after that, there is a need for you to do reverse convention of the transform coordinate for you to get your latitude and longitude, and then you do projection. But when you come to the AI, assuming I want to do coordinate transformation in 3D with the AI, what I need is my input data. So over here, I'll use the latitude, longitude, ellipsoidal height of the WGS84 to serve as my input data. Then my target is to be able to use these input variables to predict my latitude, longitude, and then ellipsoidal height. So you realize that it is just one step, and then you are getting your transformation result in geodetic form. The moment you get the transformation result in the geodetic form, you do your projection. So you notice that the processes that you must go through, the mathematical formulas that you need to write in order to push to get the result has all been eliminated. The process has been shortened for you because the AI do not need prior mathematical underlying function to be able to give you the result. So the process of you doing forward convention, get it in XYZ, and then after getting it in XYZ, you apply transformation model on it to determine parameters. You use the parameters to transform, then you do reverse convention. All these things have been eliminated. So here you feed in the data, you now get your latitude, longitude, ellipsoidal height result. You push it onto the transverse Mercator, you get your eastern and northern coordinates. Then you do your statistical analysis. So in the AI procedure, first of all, you must have a data. So normally in creating an AI model, we say you must have training and testing data. So the training data are actually the data set that you want to use to create the model. Then after creating the model, you must independently assess the validity of the model that you've created. And that is where you need the testing. So you specify your input and target data, but you do data partitioning so that you can have training data where you are going to use it to train and develop the model, and the testing data to test it. Then the next one is data normalization. Usually, you will agree with me that when you look at coordinates in itself, you can have easterns, northerns, and you see that the eastern values and then the northern values, the variability, the variation between them is quite large. Therefore, there is a need for us to try to bring all the input variables onto a common scale. And to do that, that is the data normalization. And this helps to speed up the training process of the AI or the ANN model that you want to create. Now, the moment you do data normalization, the next is what? The network configuration. You need to now look at certain controlling parameters of the type of AI method that you want to use and how you can configure it to give you the optimum result. The moment the training is done and you are able to save your optimum trained model, you have to now test it. If you are testing it, it means that you are looking at certain performance metrics. So you can look at root mean square error, horizontal error, standard deviation, etc. The moment it meets your target, then it means that your training is done. If not, you must go back and retrain by adjusting the controlling parameters. So, for example, this is a typical radial basis function neural network structure. Now, if you want to use the AI, what is going to happen is that you must first of all feed in your input data to this layer here. And then when you feed in the input data to this input layer, the system automatically transfers the data or send the data directly to this part, which we call the hidden layer. And the data will now be weighted, computations will be done, and then it will be transferred directly into the output layer, where computations will go on to, and then you get your predictions. So in the case of the radial basis function here, my input will now be the latitude, longitude, ellipsoidal height of the WGS84. And then my target will be the latitude of the war office, longitude of the war office. And then if I need the ellipsoidal height, I'll add that one too. So that becomes my target. Now, in literature, these are the methods that have been applied to perform coordinate transformation. The GMDH stands for the group method of data handling. The radial basis function neural network is the RBFNN. The BPNN is the backpropagation neural network. GRNN is generalized regression neural network. RNN is the recurrent neural network. CNN is the convolutional neural network. The MAS is the multivariate adaptive regression spline. The ELM is the stream learning machine. The SVM is the support vector machine. The LSSVM is the least square support vector machine. The AMPHIS is the adaptive neurophagy inference system. Then recently, there is a work that has been done that considers the interval prediction, where they were looking at the uncertainty levels. So far in literature, these are the methods that have been explored to test its capability as an alternative procedure for coordinate transformation. You can get all the literature on that. Now, let's look at the examples of some case studies. Now, when you look at this paper, this was carried out in Turkey, where they considered the European datum 1950 and then the WGS 84. And this is a research work done by Bayram Tegat in Turkey. Now, from the abstract, it was clearly stated that the backpropagation artificial neural network was able to transform the 3D coordinate XYZ more accurate than the Molodensky-Betkas method, and therefore is useful for 3D coordinate transformation between the European datum 1950 and that of WGS 84. So this is a sample of the results that was obtained. Now, when we look at this paper, this is also one of the recent papers just in 2022 that was published by Ahmed, and he was using the artificial neural network for 2D coordinate transformation. And he considered the Clark 1880, the WGS 84, and then the International Terrestrial Reference System 2008, because these are the reference systems that are used in Iraq. So he also concluded that the ANN is a useful tool for 2D coordinate transformation. In his paper, he also considered other conformal models, that's a 2D conformal least square. Now, when you look at the least squares, the root mean square error for the easterns and that for the northerns, you realize that that of the ANN was very small. Then this is also a paper written by Tierra, my mentor in Ecuador. He was also looking at the South American datum of 1969, as well as comparing it with other established reference datums in Brazil. So in his work, what he did was to look at the official parameters that are being used, the results that was obtained with these new parameters, and then the new regional parameters, as well as the ANN. So when you look at this column here, which is giving you the ANN result, you realize that the arithmetic mean, the standard deviation, the minimum difference and maximum difference for the ANN were very low as compared to the conventional models. There's also a paper written by Gulu, where they were considering the Nile River, an old map where they want to do georeferencing, and they also employed the ANN method. Then in Egypt, Shambaki has also done a research where he also used artificial neural network and then compare with the conventional Helmut and Molodensky methods. And at the end of the day, there was an improvement in the coordinate transformation results by the ANN as compared to the conventional technique. And these are some of the results that were obtained. Now, when you look at the result of the ANN here, you will notice that the ANN actually achieved the best. And then when you look at the checkpoint, which is actually the test data, it also showed that the ANN is a very reliable tool for coordinate transformation. There's another paper by Gulu again, which was written in 2010, which he also considered the Turkish National Geodetic Network datum, the ED50 and then the WGS84. And at the end of the day, the radial basis function neural network that was used was able to approximate the data very well and give better transformation results. And when you look at this diagram, you realize that when you look at the mean error, the ME over here, the affine result and that of the radial basis function, then when you look at the root mean square error, you see the affine and then the root mean square, the radial basis function neural network root mean square error. You see that the RBFNN was the most dominant and potent method. Now, we will say that, so what are we doing in Ghana? Yes, in Ghana, we have also done a couple of works. The first one was to also try to ascertain the performance of artificial neural network for planimetric coordinate transformation. So over here, we use the Clark 1880 and then the War Office ellipsoid, and then we tested the ANN methods on it. And the results confirm what has been reported in literature. Again, we also tested the least square support vector machine model to see whether it can also serve as an alternative transformation model with regards to coordinate transformation. We have also worked on the extreme learning machine technique for 2D cadastral coordinate transformation. We compared with the conventional conformal models and affine models, and the extreme learning machine was the best. We have also looked at performing coordinate transformation with data scarcity or with sparse data, where we considered the k-fold cross-validation approach as a resampling method that needs to be employed when you have limited data and then using coordinate transformation. We have also looked at the group method of data handling approach for horizontal coordinate transformation. We have also integrated total least squares and radial basis function neural network for 3D coordinate transformation. These are all works that have been done directly with respect to the Ghana Geodetic Reference Network. We have also ascertained the capability of artificial neural network for the forward convention of geodetic coordinates. Because when you want to do 3D coordinate transformation, you will agree with me that the first step is for you to do forward convention. So over here, we assess the capability of the ANN as an alternative tool that can be employed for the forward convention. We have also implemented a multivariate adaptive regression spline for 2D coordinate transformation. All these works are pertaining to the Ghana Geodetic network. Now, conclusions. There is a paper that was written in 2021 by a group of professors and doctors who work in Germany, and they were looking at machine learning and geodesy, a survey. So in this particular paper, certain conclusions have been drawn as to the machine learning or the AI being more flexible, and also because of its non-parametric nature, is able to handle data properly, and then also give better results as compared to the classical models. So all these things that we are presenting is something that is going on. People are still researching into it, and students that have joined is something that they can take it up and also champion the use of AI and machine learning in the field of geodesy. Then when we look at the transformation result that we've presented so far, you will notice that the AI, one of the biggest trademark is that it is able to improve the transformation accuracy that we normally get from the conventional methods. Now, for future direction, I remember in my PhD, I wrote a paper and submitted to Journal of Surveying Engineering, and they asked me to compare the AI to the distortion grade coordinate transformation that is normally done. So when you look at the methods that have been utilized, you notice that most of the standalone methods have been used, but nobody has really considered using the AI as a distortion modeling technique. So normally what is happening is that because the conventional techniques are handicapped, now when you perform the transformation, let's say Bessawov, you need to move a step further by doing the grid-based transformation to improve the result. Now, how will the AI perform? Yes, in terms of applying the Bessawov, the Molodensky's, the Vase, the geocentric translation model and so on, and comparing it with the AI as standalones, the AI performance is the best. But there's a need for us to use the AI as an interpolation method in a distortion system, so that we can also compare when we use the AI as a distortion modeling technique, how is it comparable to the other interpolation methods, the radial basis function interpolation methods, the minimum curvature interpolation methods, and so on and so forth. So this is something that has not been researched in literature. Then in literature too, you realize that all the methods that have been used are actually based on what? Standalone or single AI models. So you take backpropagation neural network, radial basis function neural network, support vector machine. These are all models in their classical developed state. Therefore, for future directions, there is a need for us to look at optimizing the performance or improving the performance of the standalone methods. And how do we do that? So for example, when you take the backpropagation neural network or multilayer perceptron trained with backpropagation, you will notice that there are certain controllable parameters that we consider, like the learning rates, the number of hidden neurons we need to use, even the activation function types we need to use in the hidden and output layer, and so on and so forth. How do we automate the process? How do we apply optimization algorithms so that the initial weight or the weight that is assigned to the input data that we feed to the backpropagation system could be the optimum, and then also improve the result that we are getting with the standalone methods? So that is the optimization. So we look at how we can optimize the backpropagation neural network, which is using a gradient descent optimizer in its original state. And we know that these are optimization methods that are good, but they are slow in convergence and can also give you local minima solutions. So we can look at that. Then clustering. If you have huge data sets and you want to use it for AI transformation work, there is a need for us to also look at a clustering area where the data can be partitioned, the similarity among them. So the data can be partitioned into different groups, and then models can be created for each partition. And this will even enhance further the transformation result that we've been getting so far. So this is for us who want to continue research in coordinate transformation, and those who are also interested in venturing into coordinate transformation, where they think that, okay, maybe the methods have been exhausted, but no, there are still a lot of things that we need to explore in the area of the artificial neural network. On that note, I say thank you for your time, and I'm most grateful.